So this is part 5 of the course, described as ideal gases. And in this part of the course, what we'll do is we'll introduce gas laws. These are fundamental laws that govern the behavior of gases in terms of pressure, temperature, and volume that were formulated around the 1700s. We will then introduce the ideal gas law, which is a law that can be applied it's based on the gas laws, and it can be applied to a range of gases that operate under certain conditions for us to measure the relationship between the pressure, temperature, and volume rather than using the property tables. Then we will move on to introducing properties called specific heat capacities. And what they do is they help us measure enthalpies and internal energy values for those range of gases as well. So what do we mean by ideal gas? Well, an ideal gas is a hypothetical concept. It's theoretical. And it's a gas that acts in an ideal way, and a gas in which we can apply a very simple formula to identify that relationship between pressure, temperature, and volume. If we were to look at the atoms and molecules in a gas, we'd see that the particles are colliding off each other. There's a lot of molecular kinetic activity going on in there. And it's that interaction between the particles that give the gas its pressure. But it's very difficult to model all that mathematically what's going on. So for certain gases, under certain conditions, we can simplify all the activity that's going on there based on the kinetic theory of gases and apply the ideal gas equation too. So we're assuming that these particles are acting in an ideal fashion. So ideal gases are idealized and imaginary, as I said. Substances that are used to model the behavior of gases over a wide range of possible thermodynamic states in terms of pressure, temperature, and volume or specific volume. An ideal gas follows a set of assumptions based on the kinetic theory of gases that simplify the complex interaction in the gases. So some of the assumptions that are made is that the gases consist of randomly moving point masses having a velocity and a momentum. Gas molecules do not occupy any volume. There are no intermolecular attractive or repulsive forces, and particle collisions are perfectly elastic point collisions. In reality, none of this is true. So we just can apply these simplifications, to a range of gases under certain conditions, and then formulate this ideal gas law that we can use to calculate the relationship between pressure, temperature, and volume, rather than using the property tables. So which type of gases, what range of gases can we apply the ideal gas law to? Well, the ideal gas equation should be used when gas behaves ideally, and it behaves ideally at low pressures, typically less than 1 to 2 atmospheres. It also acts ideally at high temperatures, well above the gas boiling point, and when molecules are small and non-interacting. Examples would be noble gases like oxygen, nitrogen, and hydrogen. So anything that's going to reduce the activity between those gas molecules. So if the pressure is less, there's more room for the gases, the particles to move around. So there's less collisions. At high temperatures, we're spacing out the gas as well. So there's less interaction. When molecules are small and non-interacting, you get the same effect. And when densities are low, in other words, specific volumes are high, then we also have ideal gas circumstances. So in contrast, we use property tables when substances do not behave like ideal gases. So they would be dense substances like water and refrigerants that are used in refrigeration systems. So these are classic examples of substances with significant deviations from ideal gas laws. So they're dense, so they're compact, so there'll be a lot of activity. Liquid vapor mixtures such as steam are substances near phase changes, in other words, boiling or condensing, also deviate from ideal gas behavior. Substances at low temperatures and high pressures, so that's opposite to what we said up here. So if the temperature is low, or if the pressure is high and it's pushing those molecules together, we're not going to have ideal gas situations, and we'd have to use the property tables in a situation like that. So a range of gases that we would consider ideal gas. Ideal gases would be hydrogen, helium, neon, nitrogen, oxygen, argon, and methane. Some gases that exhibit non-ideal behavior would be water vapor, in other words, steam, especially near the saturation dome, ammonia, carbon dioxide, and the refrigerants, which are quite dense, like R134A and so on, which are used in refrigeration systems. So the gas laws collectively combined to produce the ideal gas law. So they were established around the 1700s. So as it says here, created in the 17th century, the gas laws have been around to assist scientists in finding volumes, amount, pressures, and temperatures when coming to matters of gas. The gas laws consist of primary laws, which are Charles's law, Boyle's law, Gay-Lussac's law, and Avogadro's law, all of which later combine into the ideal gas law. So let's look at those and then introduce the ideal gas law. So the first one is Charles's law. It was formulated by a man called Jacques Charles, who was a Frenchman, and it simply states that volume is proportional to temperature at constant pressure. So we have a situation like a piston cylinder arrangement like this. If the mass is kept constant, and if we keep the pressure constant, but if we do reduce the volume, we'll find that the temperature will increase, and it's a linear relationship. So what we can say is volume is proportional to temperature under these circumstances, or V divided by T equals C. Or another way of expressing it is by saying at any point along this line, if we take the volume and divide it by T, it equals another point on the line where we take the volume and divide it by T. The next law then is Boyle's law. It was formulated by Robert Boyle, who was an Irishman from Waterford, and it states that pressure is inversely proportional to volume at constant temperature. So once again, the mass is constant here, but we're this time keeping the temperature constant. And as we reduce that volume, we'll see that pressure increases. So what we can state there is that pressure is inversely proportional to volume, or we can say that P multiplied by V equals C. Or another way of stating it is that we take any point along this line and we multiply P by V. That will equal any other point along this line. If you multiply P by V, you get the same value. The next one then is Gay-Lussac's law. Gay-Lussac's law is a gas law which states that the pressure P exerted by a gas of a given mass and kept at constant volume varies directly with the absolute temperature of the gas. In other words, if an ideal gas is confined in a container whose volume cannot be changed and the temperature is increased, then the pressure should increase proportional to the temperature. So the amount of substance in here is staying the same, the volume is staying the same, and what we're doing is heating it up, and then we should see the pressure rise directly with temperature and producing a straight line plot like this. So in this case, its pressure is proportional to temperature, or P over T equals C. or once again, take any point along here and divide pressure by temperature. It equals any point along here where we divide pressure by temperature. So the combined gas law is combining Boyle's, Charles, and Gay-Lussac's law into this simple formula here. And this law applies when the amount of gas is constant, but pressure, volume, and temperature are changing. So let's look at a simple example here. If a cold room is at 10 degrees, is sealed, and the temperature within it is allowed to rise to 20 degrees, what would be the pressure inside? So we've got the combined gas law. One relationship there, or one point to identify, is that the volume hasn't changed because it's a room and it's sealed. So we can simplify the equation as such and then rearrange to get P2 on its own. We know what P1 is, and then we can identify what the temperatures are, but make sure they're in Kelvin, and otherwise it changes that ratio. And we can get our value in bar because our pressure was in bar. Another example here, a sample of gas has initial pressure of 202.65 kilopascals and a volume of 4 liters and a temperature of 300 Kelvin. The gas is then compressed to a volume of 2.5 liters and heated to a temperature of 350 Kelvin. What is the final pressure of the gas in kilopascals? So we can see that we've got all these values here, and we put them into our combined gas equation. It's P2 that we're looking for. So when we rearrange it and work it out, P2 is 378.28 kilopascals. So we're dealing with liters here. As long as they're the same on both sides, that should be fine. But we make sure that our temperatures are in Kelvin. And another law there is Avogadro's law, Avogadro's law states that the volume of a gas is directly proportional to the number of moles of the gas when the temperature and pressure are kept constant. The amount of substance is a fundamental concept in chemistry and physics that refers to the quantity of entities such as atoms, molecules, ions, electrons, or any other specified group of particles present in the sample. The standard unit for measuring the amount of substance is called a mole. So what we can say with this is that the volume divided by the amount of substance in mole at any point along this line is going to equal the volume divided by the number of the number of moles in the gas at any other point along this line. So that there it's proportional to each other. And 1 mole is given as 6.02 by 10 to the 23 molecules given by Avogadro's number, Na. So we can take all of those laws and combine them into the ideal gas law. So by combining the relationship described by Charles, Boyle's, Gay-Lussac's, and Avogadro's law, the ideal gas law provides a comprehensive equation that describes the state of an ideal gas under various conditions. So P here is the pressure, P is the volume, N is the number of moles, as we've said, or U is the universal gas constant, often denoted by just or. I put the U in to distinguish it from the specific gas constant, which we'll come across, and then the temperature. So the universal gas constant, or, is a fundamental constant in physics and chemistry that appears in many equations governing the behavior of a gas. It's a key component of the ideal gas law and relates the energy scale to the temperature scale. So let's just elaborate on that. The universal gas constant is defined as Na multiplied by Kb, where N subscript A is Avogadro's number that we mentioned, the number of particles in a mole. And Avogadro's number represents, it says that the number of atoms, ions, and molecules in 1 mole of a substance. And K subscript B is the Boltzmann's constant at 1.380 by 10 to the 23 joules per Kelvin. Boltzmann's constant relates the average kinetic energy of particles in a gas to the temperature of the gas. So when we work it out, the universal gas constant is 8.314 joules per mole Kelvin. Another important relationship here before we go any further is that mass equals molar mass by number of moles. So we transpose that, we get the number of moles equals mass divided by the molar mass. So M is the mass of measured in kilograms. N is the number of moles of a gas measured in mole. And capital M there is the molar mass or molecular weight measured in kilograms per mole, mass of 1 mole. So the ideal gas law can come in different forms. The standard form is P multiplied by V equals N, or T, where R is the universal gas constant. On the previous slide, we have shown that N equals M divided by capital M. So that's the number of moles equals the mass divided by the molar mass. So if we put this expression in here for N, and if we rearrange the equation to get M, capital M under RU, this relationship RU divided by the molar mass is what we call the specific gas constant in joules per kilogram Kelvin, and it's denoted by R subscript S, excuse me. So this is another form of the ideal gas law. PV equals M, the specific gas constant by temperature. And if we divide across by mass, we get the ideal gas law per unit mass. So joules per kilogram. So it's pressure by specific volume by RS and T. And there's no mass on that side of the equation. So an example here would be a 2.5 litre container holds 0.5 moles of gas at 300 Kelvin. What is the pressure of the gas? So what we have as regards information is the number of moles. We can find the universal gas constant, or U, and so it would be preferable to use this form of the ideal gas equation. Transpose it to get P on its own. So we have N, we have the universal gas constant that we can look up, the temperature and the volume. So the pressure works out at 498.84 kilopascals. Another example, an empty cold room has a volume of 23 meters cubed. If the pressure inside is 1 bar and the temperature is minus 10 degrees Celsius, what mass of air does it contain? Use the specific gas constant for air at 287.1 joules per kilogram Kelvin. In this particular case, we're given the specific gas constant and we're looking for M, so it would be appropriate then to use this form of the ideal gas equation. Once again, we transpose it to get M on its own, and it works out at 30.44 kilograms. Down here, I just have an example of how to break down the units into their base units, just to make sure that there's consistency in the equation. So we have introduced the molar mass, and it can be used to convert the universal gas constant to the specific gas constant in accordance to this equation here. So the question is, where do we get the molar mass from if we need it and we want to do that conversion? A couple of examples. Let's take water, for example. The chemical composition is H2O. Each molecule contains 2 hydrogen atoms and 1 oxygen atom. Each hydrogen atom weighs 1 atomic unit, and each oxygen atom weighs 16 atomic units. So the molecular weight then is 1 plus 1 plus 16 equals 18 atomic units, or 18 grams per mole. So the molar mass of H2O is then 18 grams per mole. But in SI units, it's preferable to express it in kilograms per mole. So divide that by 1,000 and you have 0.018 kilograms per mole. Slightly more complicated version for air, you've said 78% nitrogen, 21% oxygen, 1% argon. For the nitrogen, you've 2 by 14 atomic units, so that's 28 grams per mole. For oxygen, it's 2 by 16 atomic units, so it's 32 grams per mole. And for argon, it's 1 by 40 atomic units, and that's 40 grams per mole. We multiply each of them by their percentages, so 0.78 by 28 plus 0.21 by 32 plus 0.01 by 40. It works out at 28.96 grams per mole, but in SI units, it's 0.02896 grams per mole. We've mentioned previously that for dense substances like water vapor or steam, as it's commonly referred to, um, we would use the tables and not the ideal gas law. However, under certain circumstances, we can use the ideal gas equation for dense substances like water vapor. So if we look at this graph here, it's a property diagram for water, and it plots temperature against specific volume. We have the pressure axis here, for example, in green, 10 kilopascals, and it goes up this way. So over here we've got the liquid zone. Over here is the under the dome is the mixture region, and over here is the superheated steam region. But we also have these values that are positioned along the pressure axis. And what they are percentages of error. So it's how much the value deviates. If we can consider it an ideal gas, how much value that deviates from it being treated as a real gas. So up here says the TV diagram shows the error of the specific volume between the real gas and the ideal gas assumption. So the epsilon value is calculated by measuring the specific volume for real gas minus the specific volume for an ideal gas divided by the specific volume for a real gas. What we see is that error is less significant when we're dealing with less pressures under 10 kilopascals and at higher temperatures. So over in this region here, away from the saturated dome, and also in low specific volumes. We mentioned previously, high specific volumes. High specific volume is low density, and high temperatures and low pressures all contribute to a gas becoming more ideal. So under these circumstances, over here in this region, we can treat steam as an ideal gas. The compressibility factor, let's go through this. Real gases such as water vapor exhibit deviations from ideal gases due to intermolecular forces and finite volume occupied by the gas molecules. These deviations become significant at high pressures and low temperatures, as we've said. To quantify the deviation of a gas from ideal behavior, the compressibility factor Z is often used. And the compressibility factor is defined, as we'll get to that now in a moment. But if we consider the ideal gas equation in this form here, and we transpose it to get all the terms on one side and let that equal Z, if we multiply the pressure by the specific volume for the gas and divide it by the specific gas constant and the temperature, if that value equals 1, then we can treat this gas as an ideal gas. The more it deviates from 1, either higher or lower, due to attractive molecular forces or repulsive molecular forces, then it's deviating from being an ideal gas. So what we can do is we can take our values in the ideal gas equation, work out compressibility factor, which also can be worked out by dividing the actual specific volume by the ideal specific volume. And if it's deviating from being 1, we can put it in here into our equation to correct from it not being considered an ideal gas. The van der Waals equation of state. So ideal gas law, where gases are assumed to have no intermolecular attraction or volume. And the van der Waals equation is an improvement on the ideal gas law. It accounts for real-world factors. A corrects for intermolecular forces, pressure, and B corrects for finite volume. So we assume that the particles have are points and don't have a volume, and this corrects for that. So the van der Waals equation is particularly useful for gases at high pressures and low temperatures, where deviations from ideal gas behaviors become significant. So basically, if A and B were zero, this equation here would look like this, a version of the ideal gas equation, where Vm is the molar volume, which is the volume divided by the number of moles. So it's just another version of the ideal gas equation if A and B are zero. And then if we have adjustments to make, we can use the van der Waals equation and put in A and B in there to correct for them. Okay, so specific heat capacities. Up to now, what we've done is we've introduced the ideal gas equation that can be used to identify the relationship between pressure, temperature, and volume for a range of gases under certain conditions that can be regarded as ideal gases, rather than using the property tables. But what about internal energy and enthalpy, which are values that we can get from the property tables for those other gases? How do we get them when we're dealing with ideal gases and we want to use the ideal gas equation? Well, that's where the specific heat capacity comes in. Different properties or substances, excuse me, heat up and cool down at different rates. So it's useful to have a property that reflects this, and that property is the specific heat capacity. So let's read through this. The specific heat of a substance is a measure of the amount of heat required to raise the temperature of a unit mass of a substance by 1 degree, either Celsius or Kelvin. In thermodynamics, we're interested in two kinds of specific heats. There's the specific heat at constant volume, denoted by C subscript V, and it's in joules per kilogram Kelvin. And it's the energy required to raise the temperature by 1 degree when the volume is kept constant. In other words, an isochoric process. C subscript P is the specific heat at constant pressure in joules per kilogram Kelvin. And it's described as the energy required to raise the temperature by 1 degree when the pressure is kept constant. In other words, an isobaric process. So they are defined under constant volume and constant pressure conditions, but they're applied to any process involving temperature changes when we want to know internal energy and enthalpy. So specific heats Cp and Cv are intrinsic properties of a substance and used to calculate changes in internal energy and enthalpy. For an ideal gas, the differential change in internal energy du when the temperature changed by a differential amount dt is given by this relationship du equals mCv dt. So this is an infinitesimal small change in internal energy for a very small change in temperature. But normally when we're operating between two temperatures, we'll express them as delta H, delta U, okay? So the small change in internal energy equals the mass by the specific heat constant capacity for constant volume by the temperature change. For an ideal gas, the differential change in enthalpy dH when the temperature changes by a differential amount dt is given by a similar equation except with Cp in here. If we were dealing with heat capacities per mole, we would use these equations where we've the number of moles and we've the bar over the specific heat capacity, and that's giving the units in joule per mole Kelvin. So sometimes you might see it expressed like that, So you're dealing with it per mole rather than per kilogram. So where would we use CP and CV, for example? So use CP when the process occurs at constant pressure or when you're dealing with calculating enthalpy changes. Open systems that are open to the atmosphere that involve heat and cooling, they're regarded as constant pressure processes. Heat exchangers, if there is no significant pressure drop, and once again, combustion processes and air conditioning systems. CV, when the process happens at constant volume or when you're calculating internal energy change. So closed rigid containers where there's no volume change. Compression strokes in idealized engine models. Adiabatic compression and expansion. And internal energy-based energy balances. So I'll give you a few examples of this in the applications that this would be put to. But let me just derive the specific heat uh, constant, the specific heat capacity at constant volume being used to measure the change in internal energy. For a given amount of gas, the specific heat at constant volume can be derived from the first law of thermodynamics. So this is the first law of thermodynamics. If we apply it to the illustration down here and the right-hand side of the illustration, we can say that the change in internal energy in the gas in the piston cylinder arrangement here is the heat applied to it minus the work being done by the system. So we're accounting for the energy. It's either going in as heat, coming out as work, or it's changing the internal energy of the system. When we're dealing with a constant volume process, though, the work component here is zero. So this would be the illustration on the left-hand side there. There's no piston. It's a constant volume rigid vessel. So there's no piston, nothing moving, and no work being done. So our first law equation simplifies down to du equals dq. The heat going in is changing the internal energy of the gas. So the specific heat at constant volume is defined as the amount of heat added per unit mass to raise the temperature by 1 degree at constant volume. So this is it expressed here mathematically. And if we rearrange it to get dq on its own, it looks like this. For an ideal gas, the change in internal energy du can be expressed as follows. So when we're dealing with a constant volume situation where there's no work being done, as we've shown, the change in internal energy equals the change in heat, equals mCV delta T. So that's showing us that for a constant volume process, we can measure the change in internal energy with this equation. And it can similarly be shown that the enthalpy is the mass by the specific heat constant at constant heat capacity at constant pressure by the temperature change. So a few examples. Calculate the change in internal energy when 3 kilograms of argon gas is heated from 300 K to 450 K at constant volume. The specific heat capacity at constant volume CV for argon is 312 joules per kilogram Kelvin. So this is a constant volume process, and we're given CV at 312 joules per kilogram Kelvin. We're being asked for the change in internal energy. So that's why we would use the equation, this particular equation. Delta U equals mCV delta T. And we have our values, and it works out at 140.4 kilojoules. The second example, calculate the amount of heat required to raise the temperature of 1 kilogram of ethanol by 10 Kelvin. Use the mass specific heat capacity, CP equals 2440 joules per kilogram Kelvin. It's a constant pressure process because it's open to the atmosphere. So we're going to look at the delta H, which is the enthalpy. It equals mCP delta T. Plug in our values. So 24,400 joules of heat is required to raise the temperature of 1 kilogram of ethanol by 10 degrees. So steam enters the turbine at 500 degrees Celsius and exits at 200 degrees Celsius. Mass flow is 5 kilograms per second. The CP for steam is 2.1 kilojoules per kilogram Kelvin. So the turbine is an open system involving enthalpy change. So the change in enthalpy per second is the power output. We have our temperature change. We have our CP. It's the enthalpy value we want. And we're not given the mass, but we're given the mass per second. So when we put that in, it gives us in values in joules or kilojoules per second or watts. And in this particular case, when we work it out, it's 3.15 megawatts. Calculate the pressure and change in enthalpy when 5 kilograms of nitrogen gas in a 10-liter vessel is heated from 300K to 350K. The specific heat capacity CP at constant pressure for nitrogen is 1040 joules per kilogram Kelvin, and the molar mass of nitrogen M is 28 grams per mole. So the first thing to do is to work out the number of moles. So that's the mass divided by the molar mass. So we get the number of moles here. We can use that in our ideal gas equation with the universal gas constant to calculate what the pressure is. Now we put the pressure, sorry, we have the pressure, and the change in enthalpy is the mass by the specific heat capacity by the change in temperature. And we get that value. Another example, a leak-proof variable volume closed cylinder closed system contains 2 kilograms of argon at state 1, at which the pressure is 2 megapascals and the temperature is 278 Kelvin. The system is then brought to state 2, at which the pressure is 4 megapascals and the temperature is 315 Kelvin. Evaluate the increase in internal energy and the increase in specific enthalpy of the gas from state 1 to state 2. The argon can be regarded as an ideal gas with constant specific heats CV and CP of 0.312 kilojoules per kilogram Kelvin and 0.5203 kilojoules per kilogram Kelvin. So first of all, the internal energy, the change in internal energy is the mass by the specific heat capacity constant volume by the change in temperature. And we get the value 23.1 kilojoules. The second one, we're not asked for the change in enthalpy, we're asked for the change in specific enthalpy. That's why with the small h, and that's why the M is missing, because the specific enthalpy is the enthalpy per unit mass. So we've get the specific heat capacity at constant volume by the temperature change, and it works out at 19.25 kilojoules per kilogram. And one more example, a 2 kilogram sample of helium gas is initially at 400 Kelvin and occupies a volume of 5 liters. If the gas is compressed to a volume of 3 liters while maintaining constant temperature, calculate the initial and final pressures and the change in internal energy. The specific heat capacity at constant volume for helium is 3.115 joules per kilogram that should be kilogram Kelvin. A molar mass for helium equals 0.04 kilograms per mole. Okay, so first thing to do is calculate the number of moles again. We get 500 moles, dividing the mass by the molar mass. Calculate the initial pressure. So we've got the number of moles, the universal gas constant, the temperature and volume in our ideal gas equation, and we work out our pressure. And calculate the final pressure. Since temperature is constant, we use Boyle's law. P1 V1 equals P2 V2. Transpose it, get P2 on its own, and our final pressure works out at 554.266 megapascals. So for the change in internal energy, we use this equation equals mCV delta T. However, since the temperature is constant in this case, delta T equals 0, and then therefore the change in internal energy is 0. So we only have a change in internal energy when we have a change in temperature. And similarly, for an ideal gas, the enthalpy mCp delta T equals 0 with no change in temperature as well.